Welcome again. In this presentation, we will discuss how to track steps without offsets using two DOF controllers. We will see the need for integral mode and we will see the condition for tracking steps. This is the standard controller configuration. This is known as the 1 DOF or 1 degree of freedom controller, because the same controller GC is used for tracking and also for disturbance rejection. Both the reference signal or the set point signal and the disturbance go through the same controller. Let us also recall the 1 DOF controller that we are familiar with, standard PID controller. Remember that when we have integral mode, RC of S equals 0 is 0, RC is the denominator of the transfer function. Here, because of the integral mode, when you substitute S equals 0, it becomes 0, and we will show that in the discrete time equivalent, that is in Z transform, you have to substitute Z equals 1 and the denominator will be 0 in case of integral mode. So the same controller is used for tracking and also disturbance rejection, but we may need different controllers. So we propose a 2 degrees of freedom controller. Okay, we propose another degree of freedom in this fashion, where U here is given by Tc by Rc times R. From here, this signal comes here, this signal is R times Tc by Rc minus this signal, which is Sc by Rc into Y. This control block Sc by Rc stabilizes this loop. It also rejects disturbance that can come through Y, whereas the other block Tc by Rc helps track the reference signal. This is known as a 2 DOF controller, 2 degrees of freedom controller. We can quickly see that the 2 DOF controller becomes 1 DOF if Tc equals Sc. Let us substitute Tc equals Sc, then I can common factor this Sc out, Sc by Rc into R minus Y, and R minus Y is nothing but the error signal E. This is the standard 1 DOF control law. We can also see it using this diagram. Tc is equal to Sc, so I can put Sc here and I can take this block and take this block inside here and call that Gc, which is Sc by Rc, and then R minus Y is E. We want to track step signals without any offset. We know that in order to remove the effect of steps, integral mode is required. We know this from the internal model principle that we studied earlier. We showed that for 1 DOF controller. Do we need any additional condition for 2 DOF controllers? That is what we want to answer now. Recall also the area based approximation that we derived in the previous lecture. I want you to concentrate on this approximation, the terms that come in the first column. Note that all of them have Z minus 1 in the denominator. As a result, whenever I substitute Z equals 1, the denominator will become 0. Z equals 1 means this is 0, Z equals 1 means this is 0, and so on. So that is why we made that statement, Rc of Z equals 1 is 0 whenever the integral mode is present. So let us derive the closed loop transfer function first. This is the standard 2 DOF that we considered. The expression for U is given here. U is Tc by Rc into R, which comes from the first block, and the second block gives rise to this expression. Now let us derive the closed loop transfer function. Let us write down the value for Y. Y is equal to Tc by Rc times the transfer function that comes from here, Tc by Rc into the forward gain divided by 1 plus the loop gain is BSC divided by ARC. I can simplify this, so the numerator becomes B times TC, this A comes here, ARC cancels this ARC but multiplies this ARC, so I get this expression and I have to put this R. Okay, this is what we will start with in the next slide, and the error E is given by R minus Y, reference signal or the set point signal minus the actual value R minus Y. So it is R minus Y can be factored like this, R is a common factor in both of them. I have substituted for Y from here, I simplify it, I get this ARC plus BSC come here minus BTC divided by this denominator term. We have used mixed notation that I used previously, where I have used small e and small r. What I mean by that is this: we are working completely in Z transform domain, this is what I meant, and because R is a step and I can take Z transform and I get RZ as Z over Z minus 1. Let us substitute here and using that evaluate limit n going to infinity of E of n, which is the steady state value. We use the final value theorem here and let us substitute for Ez from here. So Ez has two parts, here is the first part, the second part is R of Z, and for R of Z I will substitute from Z over Z minus 1. Now I can cancel this Z and Z, Z minus 1 and Z minus 1. What I have is the middle term, and in that I will explicitly show the argument Z, and this is to be evaluated at Z equals 1 because we are taking the limit as Z going to 1. So this is what we had in the previous slide, and recall that if the controller has an integrator, RC of 1 is equal to 0, we saw it in the summary slide. So when I substitute limit n going to infinity of E of n, I get E infinity, and I have to take Z equals 1, so I have RC of 1, but RC of 1 is 0, so this term becomes 0, similarly this term also becomes 0. So what we are left with is the term that contains B in every factor. So I can cancel this out and I get SC of Z minus TC of Z divided by SC of Z with Z equals 1, and I want this to be equal to 0 because this is the steady state offset or steady state error given by E infinity, and when I substitute Z equals 1 I get this SC of 1 minus TC of 1 divided by SC of 1. I want this to be equal to 0. That condition can be satisfied if one of the following is met, which is TC and SC are equal. This is the case of one DOF controller, or TC equals SC of 1, or TC of 1 equals SC of 1, or TC of 1 equals SC. So these are the only conditions that need to be satisfied for offset free tracking of steps with integral, and I want this expression to be equal to 0, which will be fulfilled if one of these four is satisfied. So this is the basic result that you have to remember when you discretize a continuous time controller. It is using this fact people have arrived at many different discretization algorithms. Every one of them will satisfy this. If you remember this, it will be very easy for you to analyze any discretization algorithm. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.